Let's go over exponential growth. So the basic exponential function is y equals a times b raised to the x. So in order for that to be exponential growth, a has to be positive. And also b has to be greater than 1. So when we look at an exponential growth graph, it's going to follow some type of shape like this, where each point is some factor greater than the next one. So for example, if b is 1.2, and we'll say a is 2, we have y equals 2 times 1.2 to the x. Now let's see what this table looks like. So we can look at an actual calculator and try this. So let's put this graph in. So 2 times 1.2 raised to the x. Let's look at the table, so the second table. And we have 2, 2.4, 2.88. So the question is, how do we get from these points? Well, each time we're just multiplying by this number. So 2 times 1.2 gives us 2.4. 2.4 times 1.2 gives us 2.88. And then the next point is going to be 2.88 times 1.2, which is 3.456. So each time we multiply by 1.2. So we're not going up by a set amount. Like this one up by 0.4, this one up by 0.48, this one up by even more. So the increase from y value to y value is actually increasing itself. Whereas if we have a linear graph, it goes up at a constant rate each time. So here, the jumps in y values increase linearly. It would be the same increase the entire time, or decrease. So exponential growth first has to have an x in the exponent in order for it to be exponential. And for growth, it has to be a positive number greater than 1 that is raised to the x. So very important is that exponential growth grows by a factor. So you keep multiplying by certain numbers to get a new value. So this could be, for example, compound interest. So each month you might grow by 8% or 0.8% or some value compared to the previous one. Whereas linear growth grows by a constant value. So instead of growing by a certain percentage of what was previously there, it's just always going to grow by a set amount. So maybe each month goes up by $20. Whereas here, one month it may go up by $8. Next month it could increase by $10. Then the following month by $14, and so on. So even the amount that increases by increases each month also. Whereas linearly, it's the same amount of increase each month or year or whatever time period we're talking about. Let's look at an example. So we have two savings accounts. Both of them start off with $200. One of them grows 5% annually. The other one grows by $20 annually. So we have savings account A and savings account B. Let's start with savings account B, the one that grows $20 annually. So we have year 0, 1 year later, 2, 3, 4, 5, 6, 7, 8. So this is years, and then this is the value. So it's 200 Then a year later it grows by 20, so it would be 220. Then 240, 260, 280, 300, 320, 340, 360. So each year it just increases by $20. Let's look at this account. So year 0, it's $200. Okay, then it's going to increase by 5% of that value. So let's see what that would be. So we have 200 times 5%. So by $10. So now there's going to be $210. Now again, it grows by 5%. So let's try that. 200, 210 times 0.05. So now it grows by $10.50. So it's going to have $220.50. Okay, now this is going to grow by 5%. So now it grows by $11 and about 3 cents. So let's add that to the 220.5 that we had. So now we have $231.53. Okay, now this grows by 5%. So 53 times 5%, $11.57, or $11.58, we'll say. So this gets added to the 231.53. So now we're at 243.11. So still, this looks like it's further ahead. But let's make an equation for this, and I'll show you. So y equals the initial value, 200. It's going to grow by 5% every year, so that'll be 105%, which is 1.05. So it'll be times 1.05 raised to the x. So let's put this in 200 times 1.05 raised to the x. Let's look at this table. So far we match up. And if we look at the differences here, let's compare it to the savings account, which grows by $20 every year. So far we're not growing by more than 20. If you look at the y values, here it's only about $13. Let's keep on going. So here it's about a $15 growth. Still not there yet. Here it's about $18 growth after 14 years. Now here, after 16 years, we see it's a difference of $21. Now here, look, it grew by almost $30. This is about $34 per year growth. And we see that as time goes on, from year 33 to 34, it actually grew by $50. So it may grow more slowly at first depending on the numbers we're comparing, but after a set amount of time, it's going to grow by an even greater rate, and it will eventually pass this one. So that's what you should keep in mind about exponential growth compared to linear growth. And what happens if it wasn't 5%? What if we had 8% instead? So 1.08. Let's look at this table. And we'll start back at 0. So right off the bat, it grew by $16. Then already after year 4, it grew by more than $20. It grew by about $21. From year 9 to year 10, we're at about $32 growth. So depending on the numbers, uh, the compound interest or the exponential growth will quickly pass linear growth if it's not already greater than it.